Should we start? Okay, so no more PowerPoint lectures. Now we're going to go sort of standard chalkboard. And we're going to start with special relativity. Before I do any announcements, there will be precepts tomorrow, mostly just introductory. I've got the homework worked out, but I didn't print up a copy for you, so I'll post that later today on the webpage. Everyone find the webpage okay? Any problems with that? Okay. Any other questions about procedure? The homework is due again a week from Friday. Okay, let's start. Okay, so I gave you a quick introduction on Monday. Is this white? Good. We have this fact that for Maxwell's equations, the speed of light is predicted. It's 1 over the square root of mu naught and epsilon naught. And again, this remarkable thing, mu naught is this constant that enters into the strength of a magnetic field for some current. And epsilon naught is this constant that enters when you calculate the strength of an electric field from some charge. And then this beautiful theory, and boom, out pops this number, which is the speed of light. Again, I think you guys know this, 3 times 10 to the 8th meters per second, quite fast, which is 186,000 miles per second. Okay? But so then there's just this funniness, right? That velocity is relative to what, right? If I walk along and I toss a ball and I have an arm that has a certain strength, I'm going to get a certain velocity. Now that I'm getting older, when I go to the batting cage or with the radar, it's getting embarrassing how slowly I can throw it. But if I ran forward and threw it, right, I would get to add the velocity with which I ran to the speed of the ball, clearly. That's called Galilean velocity transformation. In fact, Galileo thought about this. Not that it's that deep, but he thought about it, actually wrote about it, okay? Just a simple idea that if I'm moving and I throw something, I'll add my speed to it. I have a speed here, and it would seem to depend on whether things are moving. And yet there's nothing in the electromagnetic theory that talks about that. So people assumed that, well, we're missing some deeper understanding of electricity and magnetism, and the electric fields, which are epsilon naught has something to do with, the magnetic fields, which mu naught has something to do with, they must be due to some underlying substance in the universe, some ether, and that we haven't detected so far, but we'll somehow detect it someday. And the speed of light must be constant in that ether. And at the time, they knew that the Earth, of course, orbits the sun. But this is before they knew about galaxies. Astronomy was in its infancy. If you take a modern view, the reason I mention that, of course, is like, well, what motions are there? I mean, you can run around on the surface of the Earth. Clearly, you're not going to get moving very fast compared to that. The Earth moves at a reasonable speed. The Earth moves, anyone have any idea? It's 30 kilometers a second. Quite fast, okay? That's how fast we're orbiting the sun. In fact, the modern view is we know there's much more than that. We're in a galaxy, the Milky Way, and the Milky Way is rotating, okay? There's V of the rotation of the Milky Way. And that's on the order of 230 kilometers per second. That's how fast the Earth is moving around in a circle with the sun. The whole sun is moving around the center of the galaxy. That's 1,000th the speed of light, just about. So we're cruising. Then it turns out, if you look out in the universe as a whole, the whole universe, on average, all the galaxies are sort of, well, they're all moving away from each other, which is something we'll get to at the end of the day. But if you sort of factor that out and say, well, let's just average over, forget the overall expansion, but just apart from that, are galaxies moving? And it turns out they kind of all are. They're sort of jittering around a little bit. And we have, it's called the peculiar velocity by astronomers. And that's even bigger, 600 kilometers per second. Okay, so if you took a modern view of ether, you might say, well, the ether is sort of at rest with the sort of average of the rest of the universe, all the other galaxies. And then you would say, okay, the Earth moving in the galaxy is moving at about 600 kilometers per second. That's still a lot less than this, right? This is 10 to the 6, this is 610 to the 5 compared to 310 to the 8th. So it's about 2%, 0.2%. But okay, this may have some effect, right? So let's look for the effect. So let me work out how the effect would work out, how the effect would play out. I'm going to do some math here. You're not going to be responsible for this math. I'm going to do the math to describe the Michelson-Morley experiment. It's similar to the math we're going to jump into for special relativity, and that's why I'm going to work it out in detail, even though this is really just for, you know, sort of historical background, to see what they worked out and how they realized there was no ether. Okay? Let's imagine two cases. Let's take a flashlight, a light bulb, say, that's connected to the Earth, and shine it on a mirror that's connected on the Earth. So I'm thinking of something very simple here, just a mirror over there, and I take a light and I shine it, and the light goes out and it bounces back. Okay? Quite straightforward. Let's take, in case one, let's assume that at the end of the day, the velocity of the Earth, whatever it is, due to any of these effects, overall, with respect to the ether, just happens to be perpendicular to this. So suppose I shot the light over there, and at the end of the day, the Earth happens to be moving this way with respect to the ether. That's what I'm showing, perpendicular to the way the light goes. But we said the speed of light was c only in the ether's frame. So how am I going to analyze that? It's going to be kind of confusing in this frame because from the point of view of us on Earth, because the light is only going to constant speed in the point of view of the ether. So from the ether's frame, what happened was it was at rest while the Earth moved along. Okay? So you have a picture where the light left, the Earth moved, and then the light bounced off the mirror and came back. Okay? Pretty straightforward, right? I mean, if one of you just goes running by while I shine the light like that, in your frame of reference as you ran by, that's kind of what you're going to see, right? Okay? So we're just looking at it from the ether's point of view, and from the ether's point of view, the speed of light is c. All right? So now, if the speed of light is c, what I want to say, in this case 1, the time it takes for the light to do this is the distance traveled divided by c. But carefully, because c is constant in the ether's frame, I want the distance in the ether's frame. Ether frame. Okay? And let's suppose that the distance was L, like the distance from myself to the mirror and back. So let's just look at this little triangle. If it took T1 overall for the full loop, I didn't draw that quite as nicely as I could have. Clearly what happens in each half trip, the mirror advanced total time T1 over 2, I call it T1 because this is case 1, times the velocity of the Earth. All right? And clearly then the length of this leg is simply L squared plus T1 VE over 2 squared. It's just a right triangle, has those two sides, right? So the hypotenuse is length squared plus that length squared is the hypotenuse, square root of that. All right? So T1 is the total distance. Well, I'm going to go 2 of those. Divided by C. Pretty straightforward. I'm just playing around with geometry. Okay? If I square this equation and rearrange it a little bit, I have T1C divided by 2 squared. I multiply by 2 over C on this side. Squared the other side equals L squared plus T1 VE over 2 squared. If I rearrange this, I collect the VE and the C terms. This is T1, let me do it this way, T1 over 2 squared times C squared minus VE squared equals L squared, okay? And then it's going to be convenient, divide by C squared, take the square root of each side, and skipping one tiny step of algebra, right, I just rearranged the algebra, right? Just divide by this term, divide out by C squared also, take the square root everywhere. That's straightforward enough. 2L over C, that's just how long I might have thought the light would take if I wasn't thinking about the ether or anything. I shoot the flashlight, that's how long it takes. But if it's really going C only in the ether's frame, that's how long it takes. Okay? Are we going to see this? VE over C. Well, at the time the experiment was done, all people thought about for VE was 30 kilometers a second. That's 310 to the 4th meters per second divided by 310 to the 8th meters per second. That's 10 to the minus 4. 10 to the 4th divided by 10 to the 8th. So 3's cancel. Okay, so this term is 1 over the square root of its, I square it, but then I take the square root. It's about a 10 to the minus 4 effect. Okay, so it's tiny little effect. Hard to see. But it's worse. Well, that's one thing. The other thing is maybe what I should do, let's not just consider that. Let's consider the case where I shine a flashlight on a mirror back and forth. But the Earth is moving like this with respect to the ether, in the same direction as the ether. All right? That seems pretty straightforward. Let's just do that. Let's think about that. Again, from the ether's frame, and this is case 2. Okay. From the ether's frame, the way to look at it as that first the light goes there and then it comes back, there and back again. Okay, so when it's going there, the starting point is the light leaves, and there's a distance L. Okay, but by the time the light arrives at the mirror, the Earth has advanced. So this is the start, and this is from the ether's point of view. Okay, the start is like that. Then by the time the photon arrives, the photon, I draw with a little squiggle. By the time the photon arrives, the Earth is shifted. And the distance that's shifted is VE times T2, I'll write T for there. All right? So the photon has to go a distance of L plus this extra little bit. And using the same idea, the time it takes is the distance divided by the speed of light in the ether's frame. T2 going there is the distance L plus VE times T2 going there divided by C. Okay? I'm going to have to come back over here. It's too bad. When the light comes back, on the way back, the starting point is the light bounces off the mirror. But of course, the Earth is moving along compared to the ether. The ether is sitting there looking at the Earth. The Earth is moving, okay? Again, with this being L, this is the stop. So I start with the light at the right, the mirror. I stop when the light hits back at the flashlight. Again, there's a distance there. V Earth times the time it takes, which is T2 coming back. All right? And so the light only went that total distance. The Earth advanced while the light was going. So T2 going back is L, and I subtract off this bit because the Earth moved into the light beam, if you will. Over C. Okay? I can solve this. I have one equation with T2 in two places. Let me multiply by C. Or no, I'm not going to multiply by C. I'm just going to rewrite this. So this is T2 back from here. I'll pull this term on the other side. Equals L over C. So T2 for the path back equals L over C times 1 over 1 plus VE over C. Okay? Pretty straightforward algebra. It's a little bit tedious. The reason I'm dragging you through this, and this is just an experimental result, is this is exactly almost the same type of algebra we're going to do as soon as we really start doing special relativity. Okay? I have to solve this equation for T2. I'll skip, well, you can see quickly that I would pull this term on that side, collect terms and divide. And it shouldn't be a surprise that it's L over C. There's not room there. I'm going to keep that one result there. Erase this and write down the result for case 2. So T2 going there was L over C times 1 over 1 minus VE over C. That's just simply a result of rearranging this equation. Okay? I'm going fast. Is that okay? I mean, I suppose you don't really want to see me do all the algebra all the time. Or do you? I don't want to go so fast and you get lost on the first day. Okay? I don't want that. No feedback? Anyone think I'm going too fast? Okay, good. All right, so then if I just combine these terms, the total time for case 2, just as a reminder, so case 1 was the the light going to the mirror and back. Case 2, I just have to add this. This is a multiplier. I have to add that and that. You know, it's the time to go there and the time to come back. Okay, so that's L over C times 1 over 1 plus VE over C plus 1 over 1 minus VE over C. Okay, that's L over C. I'm going to have to combine denominators. So I multiply that by that. So that's 1 plus something times 1 minus something, which is 1 minus the something squared. In the numerator, I have, from this term, I get 1 minus VE over C. On that term, I get 1 plus VE over C. The VE over C terms cancel. 1 and 1 is 2. 2L over C, which is the naive thing that would happen if there were no ether, times 1 minus VE over C squared. Okay, so that's T2. Whereas this was T1. So remember, that's case 1. And this is case 2, where in both cases, the Earth is going sideways. Okay, so it wasn't as simple as just observing that this was a small number. It wasn't that simple. It turns out whether I'm going perpendicular to whether the Earth is moving perpendicular to the ether or parallel to the ether, there's an effect both ways. Both times it's a little bit complicated to calculate. Actually, it's very similar math, 2L over C, 2L over C, the naive this time. But then this correction term, which is almost the same, except one time it's got a square root and one time it's not. Okay? So actually, if I want to go for if I want to measure the ether, actually it wouldn't have done to just try to deal with this, because I don't really know C that well. What I need to do is I need to look for a difference between that and that. That was the key. If I want to prove that there's an ether, I've got to, in a very good way, show that there's this direction in space, and if I go perpendicular to it and I go parallel to it, I get a different answer. And so people recognize that. Again, because this term is small, sorry, when I say this is small, let me speak a little more clearly. It's the 1 over 1 minus the square. Let's look at this term. It's a little simple. At least I don't think the square root. 1 over 1 minus this thing. This thing is 10 to the minus 4. I square it, it's 10 to the 8th. So this is basically 1 over 1 minus 0.001, right? So 1 minus that is 0.99999, 1 over that is 1.000000001, okay? Okay, so it's just what you thought, but a part in 10 to the 8th bigger, okay? And this is just what you thought, but a part in 10 to the 4th bigger, okay? And so the thing is when people originally tried to measure the speed of light, they maybe could have seen this effect, but you know, there's no way. I mean, light is so fast, measurement equipment, So how would you do it? Well, I've basically drawn the setup. Actually, in physics in general, in fact, all branches of science, but physics love to exploit this. If you want to measure something tiny or subtle, what you always want to do is, if you can, is design a clever experiment that measures the difference between two things. And it can get rid of all sorts of hard things to do if you want to really measure the absolute amount of something. So what we do, it's called an interferometer, which you may have heard of. Take a beam of light from a flashlight, say. You hit a half-silvered mirror at a 45-degree angle. So this is a mirror that bounces somewhat of the light back. Let's basically half the light go through and half the light bounce back. You've put it at a 45-degree angle. Some of the light goes straight through. Some of the light ends up going like that. Okay? Then you put full mirrors here and here, and the light comes back. Just like I did case 1 and case 2 on purpose. I did this analysis. Some of the light goes through, some of the light reflects, but some of the light comes this way. This way. Always squiggly lines for photons. And you put some sort of observation device here. I'll do what the astronomers do. Whenever they say, I looked at it, they draw an eyeball. Okay? So that's an eyeball in my bad drawing. All right? And what happens? The point is this, that effectively the light comes out and it's this wave. You've split it into two paths. The light goes different distances in these two paths. They might both basically be some length L, but of course they'll never be exactly some length L, exact. They come back, and you do know, I hope, about interference of light, constructive and destructive interference. If the two light rays, I'm going to rotate the drawing over here, if the two light rays, as they come to hit this eye, or some observation device, a piece of paper, if they're perfectly aligned, then they'll constructively add, and you'll get twice the amplitude, 4 times the intensity. If they're completely anti-aligned, so that instead of like that, this guy has hopped a phase, and this is going up and this is going down, etc., they'll completely destructively interfere, and there will be no light. Okay, that's kind of an amazing thing about waves. Okay, it's how noise-canceling headphones work. Or if they're shifted a little bit, you'll see something in between. Okay, and so the point is, you can measure a delta L, which is comparable to the wavelength of light. You can tell that these things effectively went a different distance. Now, I calculated a time difference. A Bill Gates visitation. I calculated a time difference, not a distance difference. He didn't like that. But this time difference amounts to, in some sense, that there was a path length difference. And that will cause a length difference, which is the time times the length. So by being able to have a really good sensitivity to this tiny wavelength, and what's a wavelength like? Half a micron. Yellow light is 5.6 times 10 to the minus 7 meters. And so I can measure in a really precise way any distant difference between going in this path and that path. And what matters here, where this was a number 10 to the minus 4 and that was a number 10 to the minus 8, when I work this through, what I see is that I can compare lambda to L, and that's the same fraction. And since I can make this 10 to the minus 7, and that might be a couple of meters, I can do this with a precision of around 10 to the 8th. Enough to see even this small term, certainly enough to see this term, which is 10 to the 8th for the one arm, and 10 to the minus 8 for the one arm, and 10 to the minus 4 for the other. There's also a beautiful thing about it, and this is where Morley comes in. So Michelson was the physicist, and he was thinking about all this and wanted to do this experiment. The beautiful thing about it is if you do this experiment, we don't know which way the ether is. What they did is they said, well, we'll do the experiment, and then without touching the apparatus, I'll switch the role of the two arms. So here I had the Earth going that way for the analysis I did. But then what I want to do is just rotate the whole system so that now, I change which arm is perpendicular to the Earth and which the Earth's motion, and which arm is parallel. So Morley was a chemist. He had a big vat of mercury. So they took this apparatus, and there's a model down in the foyer down below. So this big interferometer is called the Michelson interferometer. He invented this technique. Okay. And they put it on a vat of mercury and they rotate it slowly, okay? And so then if the Earth is moving with respect to the ether, you'll see the one arm and the other arm have these two slightly different time or effectively length distances, and you'll see the interference pattern change. And so actually, other people have been trying to do this. Michelson's contribution is he just did it a lot better than anyone had. And so for the first time, he showed that if there was a velocity of the Earth with respect to the ether, it was much smaller than I erased it, but the known 30 kilometers a second that the Earth is rotating around the solar system. And so then that just that killed it. Actually, some people tried to keep it going for years afterwards. There was all these questions. Well, if there is an ether, maybe it drags along with the Earth. Maybe it's stuck in a room. If you have a room, the ether is stuck in the room, and that's why you never see an effect. But eventually, everyone realized there is no ether. Not only was it was kind of a pulled out of thin air idea anyway, but there is no ether. Okay, so there is no ether. I don't know. What do you say about that? Frankly, people had no idea what to say about that. Michelson did that. Here, case 1887. Einstein, in sort of a singular It's rare in science where people do something just completely out of the blue, all by themselves. And special relativity, it wasn't completely out of the blue and completely all by himself, but probably as much as any, certainly in physics, more so maybe than anything ever in physics, he really did pretty much work alone and just come up with this. He sat and thought hard about what it might mean if the speed of light is truly constant for everybody. That there's, you know, he took seriously the idea that other people, I mean, they didn't know what to do with the ether not being there, but, you know, how could it be that if I'm walking along or running along or I'm on horseback or in a train, they had trains back then, and I shine light, that it somehow doesn't also acquire the velocity at which I'm moving? You know, how could that be? And Einstein said, well, let me just say that it doesn't. Okay, so then things get pretty weird. And that's what we're going to work through. He worked on this for a number of years and then pretty much came out with a fully formed theory. It's called the special theory of relativity. Special in the sense that, I wonder how much he actually, how much he anticipated this. Or if it came, I don't know if the title came out at the time, but the term special relativity applies to this theory, which has to do with electricity and magnetism. That was the origin of it, but then it turns out to do with motion. And then there's the general theory of relativity, which he came out with. So the special theory of relativity, I think, is 1906. In 1919, I think it was, he came out with the general theory, which is about gravity. Okay. So we're just going to talk now about the special theory of relativity. We're just going to mention the general theory of relativity briefly later. Okay. So I'm going to pick a standard setup. We're talking about special relativity. It's the same that's in the book. We're always going to talk by convention or for fun in this class about a spaceship. Why a spaceship? I don't know, just be fancy. And also because if we want this to have any degree of reality, all the effects from special relativity are only going to show up if we have velocities which are comparable to the speed of light. All these special relativistic effects exist all the time when I'm just like walking around. But if my velocity is much less than the speed of light, it's essentially immeasurably small. All right, so if I put it in a spaceship, we can pretend the spaceship might be going some appreciable fraction of the speed of light. So here's Anna, who's on the spaceship. So we'll always have Anna on the spaceship. And here's Bob sitting on the ground watching Anna go by. Okay? So the simple thing is, if Galileo were right, and Galileo did nothing more than state what was physically obvious to anyone whose central nervous system developed at a non-relativistic speed, he says, okay, let's say Bob turns on a flashlight. So let's label Bob over here. Bob turns on a flashlight with a speed c. According to Galileo, Bob sees c, okay? Anna sees what? See, Bob's going along, Bob's sitting here and emits the light. Anna's going fast compared to the light, so she should see the velocity reduced. Okay? It's as simple as that, right? Because she's racing past him when he shoots the light. Einstein says no, there's no ether. They both see C. Right? I just wrote down what I said. Okay? But that is really where, that is, something has to give. Something has to give. And it turns out our notions of time, space, and energy all give. Okay? So let's develop that. All right. Let's do a little experiment, sort of like what we just did, thinking about the Michelson-Morley experiment. Here we have Anna. I'm just going to call her A from now on. And she's going to do the bit with a light bulb Let's quit pretending they're flashlights. Light bulbs are easier to draw. And she turns the light bulb on, and she watches light go some distance and come back. Okay? And it goes a distance L. All right? And she's moving, as always, at some speed v with respect to Bob, who's sitting on the Earth. Okay? What Anna sees is straightforward. Let's let her think about the time it takes for the light to go up and down. It goes a distance L up, comes a distance L down. Time is distance divided by velocity. Anna sees, indubitably, 2L over c. Okay? What did Bob see happen? Now you'll see why I drugged you through all the math of the Michelson-Morley experiment. Bob sat here and watched this develop. Bob had to see the following scenario. He saw the light leave Anna's light bulb, travel up, hit her mirror, travel back down. He and Anna definitely agree that there's a distance L there that it went. But he saw it, I mean, he watched this thing happen, and so he saw her spaceship move, and sort of the half distance it moved was whatever speed Anna is whizzing past Bob with times time, which is the total time Bob saw the whole thing take divided by 2, right? So in half the time it moved v t over 2, right? Okay? And again, if we want to talk about times, and we're saying, of all things, bizarrely, time might not be constant, space might not be constant, but a velocity is constant, then I better, again, measure time by dividing distance over the speed of light. Okay, so this distance here is L squared plus that bit squared square root, and there's 2 of them. So it's 2 L squared plus V TB over 2 quantity squared divided by C. Okay? So let's figure out what TB is. I'm going to rearrange. So TB times C over 2 squared equals L squared plus TB times V over 2 squared. Collecting terms, TB over 2 squared times C squared. And this term I bring over, it's minus V squared, right? Equals L squared. This time I'm going to be a little more explicit about it than I was earlier. Divide both sides by C squared. Take the square root of both sides and rearrange. TB equals 2L over C times 1 over the square root of this thing. I've divided C squared through, so it's 1 minus V over C squared. All right? That's what Bob measures. We write it up here. Anna measured 2L over C. So overall, I can say that's sitting there. The time Bob measured was the time Anna measured times this factor. The algebra is a little bit tedious, but in some sense, for the profundity of the result, fairly straightforward. Remember the first time I saw this, I'd known that formula from a popular book I read earlier. I was kind of blown away that you can derive it this easily. We've just derived it. This is the famous time dilation. Okay? Let's think a second. This factor, let's think a second about what that result is saying. Let's look at this term, square root of 1 over 1 minus v over c squared. It is going to appear over and over and over and over again. And if you're using big chalk and if your handwriting is as bad as mine, and I apologize, holler if it's getting where you can't read it, okay? You don't want to keep writing that. So we give it a symbol in physics, we call it gamma. And if it's a big, important, and subtle and deep signal symbol result, we give it a Greek symbol. If it's kind of a simple thing, we give it A, B, C, D, or whatever. So this is an important result, we call it gamma. All right? What is gamma compared to 1? It's 1 over 1 minus v is always less than c, okay? Which is a result we'll come to. So this is 1 over a number less than 1, so that's greater than 1, right? And more to the point, versus v, if this is the speed of light c, I think of gamma versus velocity. It starts out at 1. If the velocity is much less than c, say like a meter per second, where c is 10 to the 8th meters per second, and this is 1 minus 10 to the something that's 10 to the minus 16. So it's utterly close to 1. I take the square root again, it's part in 10 to the 8th. But as it gets close to, as v gets close to c, that starts to blow up. And of course, if v over c gets very, very close to 1, or if in principle it got to 1, this would be infinity. So it's just shooting up like that. All right? So actually, in relativity, rather than talking about a velocity, if you have something that's close to the speed of light, it matters a lot whether it's 99% the speed of light or 99.99% the speed of light. And it's kind of tedious to talk about something moving at 99 or 99.9, etc. We just talk about gamma. It was gamma 1 or 10 or 100 or 1,000. So something that is ultra fast, ultra close to the speed of light might have a gamma of 10 to the 5, 10 to the 6. And that's a better way to talk about it. So what we just said was that TB was gamma TA. Bob saw more time pass than Anna. And the amount of time he saw pass compared to Anna depended on the velocity between the two. And the faster Anna went, the bigger this disconnect. So let's repeat that. Bob saw more time pass than Anna. Okay, so that, if you guys went whizzing past me like that, I would say more time passed for me than you. So I would say time ran slower for you. Time ran slower. So we don't even have the same concept of time. And that's such a bizarre and deep thing, and yet it comes from one simple thing. I just follow the logic of the fact that the speed of light was constant. And there I am. Okay, let's do one other thing. There's one other sort of canonical first result from, this is the first big result from special relativity. It's called time dilation, if you will. Time dilation in the sense that if you go whizzing past me, time slowed down for you. So basically you guys can go running past me and you get to live longer, effectively. Okay? Which is bizarre, and it's true. It does work. Okay? The experimental proof has been seen many, many, many times. Experimental proof, obviously, I can't see it for any speed that you can run or I could run. There's subatomic particles called muons, which are these exotic particles created in interactions of high energy particles. They're like an electron but heavier, and they decay into an electron and a neutrino. They only live 2 microseconds. Okay? And they're created in the upper atmosphere amongst other things. You can create them in accelerators, but they're created in the upper atmosphere by cosmic rays. That's particles from outer space, mostly protons. They hit a hapless nitrogen atom, kersplat. You get a bunch of stuff, including muons. If you think about just the speed of, even if the things are going at essentially the speed of light, almost c, okay, 99.9% the speed of light, times 2 microseconds, they wouldn't make it to the ground. Just, v times t, they don't live long enough, because in 2 microseconds they spontaneously whoop, up and die and break into an electron and a neutrino. But they all make it to the ground. Why? Because they're going fast. We're sitting here stationary, they're going very fast, time is slowed down for them. These muons come down, they have big gammas. They have gammas of 10 to the 5th. While you've sat in this class, I guarantee you, some number of muons have gone through you. Okay, there's about one in your body about a minute, maybe even a little more than that. And the odd one has like a gamma of 10 to the 5, 10 to the 6. And so they live 1,000,000 times longer than they would if they were just at rest as they go through you. And they go down into the dirt. And that's been experimentally measured over and over and over and over. There is no doubt. This is real. This happens. Time slows down. All right. I've only got a couple minutes left, but the second thing I want to derive is very straightforward to derive. It's a very slippery derivation, but it's only 2 lines of math. Okay? Let's have Anna race past Bob in her spaceship. Her spaceship is a length L. Anna went and measured it. She measured L Anna. Okay, and it's going with a velocity v. And Bob's sitting here and he watches her go by. All right? Once again, let's talk about a time from a velocity and a distance. The time it takes for Anna to race past Bob, let me see, it's a velocity divided by distance, right? No. I'm being very simple. Very simple. A time is a distance divided by a velocity. All right. Now that's that's what we did. The setup here is important. I chose to think of it that way. The time it took for her to go from here to here was straightforward. She's measured her spaceship. She goes v. What could be what could be more straightforward? Okay. Bob, on the other hand, says something similar. He may not measure, and this is why I labeled it not L. I said L Bob, L Anna, because it turns out they're not going to agree on distance anymore either. Bob sees her go past with some apparent distance, which is the size of her spaceship. He waits between the time of this point and that point. She goes past, and he says that. What could be more straightforward? Here's where I'm going to say something tricky. Anna sees Bob is going slower. Bob's racing past her with a velocity v. So Anna says, she says, time for Bob, runs slow. So if Bob has some time, I have more time, because gamma is greater than 1. Okay? Or when we do deltas, same story. Okay? So she's going to say LA over V, that's just delta TA, is equal to gamma LB over V. V. Velocity cancels out. The length measured by Anna is bigger than the length measured by Bob. We usually put it the other way around. We say Bob measured Anna's spaceship as contracted. Bob sees time dilation. He sees Anna as running slow. He sees Anna's spaceship as short. Now, I threw you a fast one. Bob sees Anna as running slow. To derive this, I said Anna sees Bob as running slow. Did you notice that? Both are true. If you guys are running past me and I see you as slowing down, you guys are seeing me go past you. You see me as slowing down. Who's to say who's at rest? Okay? It's actually funny. I mean, the theory is called the special theory of relativity. And in some colloquial sense, people will say, oh, everything's relative. There's these bad people out there that think everything is relative. That's not, in relativity, actually, it's not like that at all. You think very, very carefully, and both sides are going to agree on some rules. And no side is special. So if two people are just simply moving past each other, they're both going to think that the other side is going slow, and they're both going to think that the other side is contracted. However, when I derive this, if I used, look at that, what I wrote down. Isn't that the opposite of what I wrote down there? It's the other way around. Now, it is true that both, I could write it either way because they both think the other side ran slow. However, if I'd used this equation and come to this point, I would have come up with L with a gamma on the other side, and that would have been actually a wrong result. Okay? So stuff is getting kind of weird. So I'm leaving you with a paradox as I close right now, that I have to think pretty carefully. And it turns out the result, the answer is going to come, I have to think carefully about what were simultaneous events. And the way I analyzed this problem, I had to look at Anna's view of Bob's time. I could not look at Bob's view of Anna's time. And the reason for that is a little bit subtle, and I can't explain it in the next 10 seconds. So I'm going to stop. But that'll be the topic for next time.